All right, people, we are getting close. Let's take a quick look at question number 5 here. It says, calculate the mass of silver sulfide produced when 125 milliliters of 0.200 molar silver nitrate is added to excess sodium sulfide solution. Whew. Okay, so a little bit different type of stoichiometry calculation here. We're dealing with concentrations of solutions. And additionally, we're not given a chemical equation to work with. So the very first thing we should do is write out a chemical equation so we can tackle this problem. Let's see, we've got silver nitrate, AgNO3, reacting with sodium sulfide to produce silver sulfide. And although we're not told directly in the problem, our other product here in this double replacement reaction is going to be sodium nitrate. Now, we have to make sure that we've got a balanced chemical equation here. As I do a quick scan, I can see that I need to put a coefficient of 2 in front of my sodium nitrate to balance out my sodiums. And then I'd also have to put a 2 in front of my silver nitrate to balance out both the silver and the nitrate ions. So our relationships here between all of the reactants and products are 2, 1, 1, and 2. We've got a balanced chemical equation to work with, and now we can begin to solve this problem. First thing we need to recall is the molarity formula here, which is moles per liter. And we need that so that we can convert the volume and concentration that we're given in the problem to number of moles. Again, the coefficients in this equation, in all equation, represent ratios in moles. So if you're not given moles in the problem, you've got to go to moles first. So if we take our molarity here of 0.200, and our volume here, again, be careful that you convert it to liters. I'm going to do that in my head because I'm a genius. We can solve for the number of moles of silver nitrate in this 125 milliliters simply by doing a quick multiplication, which will give us 0.0250 moles of silver nitrate. Okay, now I bet you're feeling really good about yourself, and you should, but unfortunately that doesn't solve the problem. Getting moles of silver nitrate is only the first step. Again, we're looking for mass of the silver sulfide that was produced. So as we look to move forward, we're going to start now with that 0.0250 moles of silver nitrate. From silver nitrate, moles of silver nitrate. Whoops. We can go to moles of silver sulfide. And then from moles of silver sulfide, we can go to grams of silver sulfide. Again, as we think about the relationships here, moles to moles is going to come from the balanced chemical equation. For every 2 moles of silver nitrate, we're going to form 1 mole of silver sulfide. And then the relationship between moles and grams comes from our periodic table. Our number of grams is 247 for every mole of silver sulfide. And then it just becomes a matter of busting out our calculator to solve. And when you do that, you get an answer of 3.10 grams of silver sulfide. Boom. Okay, we're going to do some seriously rough estimation here. If I took my 0.0250 moles of silver nitrate that I started with and converted that to moles, or estimated the number of moles of silver sulfide that would form, I would estimate, well, I would get 0.0125 moles, but I'm going to estimate here 0.01 or 100th of a mole. And again, just sort of bear with me here. You need to be really familiar with and really comfortable with estimation. And, a 100th is going to be a heck of a lot easier to work with. If I took 100th of 247.8, I would just have to move my decimal a couple of places to give me 2.478 grams, which is definitely a little bit less than what we ended up with, the 3.10. But again, we sort of estimated a little bit less than the 0.0125 moles. So again, this is just sort of a rough estimation and a really great thing to practice doing before you take the test. That multiple choice section is going to be a killer if you can't estimate. Whew, all right, home stretch. We're here for our final problem. This last problem is, again, a stoichiometry problem with a little bit of a twist. As you see here, we're working with gases, and we're going to be asked to ultimately solve for the volume of a given gas. So let's read this problem and talk about how we can solve it. It says 0.500 liters of H2 gas are reacted with excess oxygen gas at STP according to the equation. Boom. It's always nice when you're given the equation and it's already balanced. Doubly nice. It's asked what volume will the H2O occupy at 1.00 atmospheres and 350 degrees Celsius. Okay, our first move here is to start with our 0.500 liters of hydrogen gas. Is reacted at STP. So at STP, I know that 0.500 liters can be converted to moles by using the relationship 22.4 liters in 1 mole of hydrogen gas. And that's true because we're at STP. Can't do that when we're not. So when we solve this here, we end up with 0.0223 moles of hydrogen gas. Okay, so that's the number of moles. I've just converted liters to moles for hydrogen gas. Again, it's the thing to do with stoichiometry. You've got to go to moles because your equation represents the relationships in terms of numbers of moles. As we look though to solve this problem, we're then asked to determine the volume that the H2O will occupy at 1 atmosphere and 350 degrees Celsius. So first thing, we need to figure out how much water vapor will form from this 0.0233 moles of hydrogen, again given excess oxygen. So this is just going to be a quick conversion from moles of hydrogen to moles of H2O. That relationship is a 2-to-2 relationship or 1-to-1, but I always like to write in exactly as I see it in the balanced chemical equation, which means that we're also going to have 0.0223 moles of water vapor that is formed. We're feeling good, but not quite done. We want to know the volume, not number of moles. The tricky part here is we're no longer at STP. It wants to know what the volume will be at 1 atmosphere, so that's standard pressure, but we're no longer at standard temperature. In a case like this, you've got to use Pivnert to get you through. The ideal gas law here. Our pressure is again 1.00 atmospheres. Our volume is, I don't know, we're going to use X to represent that. Our number of moles we just solved for, 0.023223 moles. Our ideal gas constant is going to be 0.0821. Again, I'm going to be super lazy here and leave out my units for my gas constant, but note that all of them but the volume unit will cancel out. And then my temperature in Kelvin, be careful here, in Kelvin is 623. So 623 Kelvin. And again, remember, we get that by adding 273 to our Celsius temperature. Then it becomes just a matter of straight up algebra. We multiply all these values together. Again, I'm going to be super lazy here. 1.1406. Make a little reminder there for where my sig figs should be. And then we're just dividing by 1.00. So our volume in liters will be 1.14 liters at that 350 degrees Celsius, aka 623 Kelvin. And we are done for the day.